Over 550 million years, fish have developed amazing ability. They can hear and smell and communicate with each other. Thousands of tiny fish swim close together, and in a school, they achieve truly great things. Tarpons and jack mackerel, both dangerous and successful hunters, launch an attack on the school. It causes brief chaos. The individual fish in the school get too close to each other. They slow down to avoid collision. Seconds later, they seem to merge into a single organism again. This natural wonder resembles a virtuoso dance. How do so many individual fish manage to move in unison with their neighbor? Stay together. Keep a sufficient distance. Move in the same direction as your neighbor. 3 fundamental rules in the swarm. So simple and so efficient. Yet researchers continue to discover new rules and forces within swarm. Jens Krause has been a fish fan ever since he was 20 years old. Today, he's a swarm intelligence researcher, eager to know how fish schools make decisions.
Fische besitzen eine ganze Reihe erstaunlicher
Fish possess a whole range of amazing cognitive abilities. They can recognize their own kind individually. They can remember places where food comes at certain times. Fish can do that individually, but even more so when they interact within a school. We speak of intelligence in creatures when they're capable of developing skills to solve problems. And our particular focus is on group behavior, because it enables them to solve problems that individual fish cannot.
There's a widespread prejudice that fish are stupid, and all the same.
Fish can differ individually in their personalities. Some take bigger risks, others are more risk-averse. Some are more social and stay close together, while others move very, very independently. And it's basically this diversity of different personalities within a school that makes the group so efficient.
So what triggers the sudden changes of direction in the school of fish? Does one leader control the school, or are there several? How can a researcher influence their decision?
I've always been interested in how swarms work. Not only swarms of fish, but swarms of living creatures in general. And what I found interesting was how new directional decisions arise, how they suddenly turn left or right simultaneously. And since it's very difficult to see in nature who does it first, we decided to build a robot fish that we can be sure will give the first directional decision. And then we can see if the others follow suit.
Taking the smallest possible school of fish with just 2 members, Jens Krause and his colleague David Bierbach look at how the real guppy behaves. Does it try to stay close to its somewhat strange-looking companion, despite a rather unusual zigzag course?
A single guppy will always seek the proximity of its conspecifics because there it's safer from predators. And that's why it follows the robot fish especially well when it's on its own. It's the only other one within reach, so that's why it follows.
David Bierbach enlarges the school of fish. Again, The robofish sets the direction. For a while, the group follows its movement impulse. A short time later, however, almost all the guppies detach themselves from the robofish.
Of course, a fish school assesses things differently. A lot of individual impressions of the fish go into the school decision, and that's why a group decision can't be dominated so easily by one fish, in this case, a robot fish.
The larger fish school clearly makes a more independent decision here. Swarm intelligence is a result of evolution. The start of a normal summer day in Hungary's oldest national park, Hortobágy. A flock of Hungarian Rotska sheep approaches the watering hole. Within the flock, the animals are more likely to find protection from predators. In Europe's largest expanse of continuous grass steppe, there's hardly anywhere to hide. Even the imposing-looking Hungarian grey cattle only feel really comfortable in their herd. A flock of starlings joins the cattle. Wherever they graze, the birds can find flies and ticks to eat throughout the summer. But there's something in the air. Every year in July, a miracle of nature takes place here, on the Tisza, a tributary of the Danube. Hundreds of thousands of mayflies celebrate a simultaneous wedding, and have done so for the past 355 million years. Until the beginning of the 20th century, Tisza flies also existed in Germany, in the catchment area of the Rhine and the Danube. Industrialization, intensification of agriculture, and straightening of watercourses caused their disappearance. Krzysztof Malnasz is an aquatic ecologist and knows that wherever numerous larvae of the Tisza fly live, the water quality is good. These ephemeral creatures eat their way through the mud. In the process, they remove excrement and rotting waste.
It sounds a bit paradoxical. It's true that the Tisza fly can only fly for a single day in its life. But for an insect, it does actually live for quite a while, considering that it spends about 3 years in the larval stage. This larva is almost ready to fly. Its wingtip is already dark. It'll probably fly out today or tomorrow. With its powerful mandibles, it digs its way from the riverbed to the surface.
They have been working towards the completion of their metamorphosis for 3 years. With a body length of 12 centimeters from head to tail, the Tisza flies are considered giants among their peers. The crucial day has arrived. The larvae swim from the riverbed to the water surface. In the air, their skin bursts open. They unfold their 4 wings and take off. But not all of them are ready yet. Thousands of chrysalises on the embankment testify to their final transformation.
First, the males swarm out. They shed their skin for the penultimate time, the so-called sub-imago, and fly ashore. After their last molt, the imago, they're able to reproduce and begin their wedding dance above the water. About half an hour later, the females follow them.
They are in more of a hurry and have already molted on the water surface. As soon as they've done so, they're fiercely courted by the males ready to mate. Their wedding dance begins. The myriads mate in unison. The swarm offers more protection to the individual insect, thus ensuring the survival of the species. It's a sight that delights Christoph every single year.
The females fly a few more kilometers upstream. That way, they try to balance out the current, laying their eggs widely scattered.
The current makes the eggs drift for kilometers, however. At some point, they sink down to the riverbed, and the cycle of life begins all over again. After the egg laying, the short life of the females also comes to an end. The carpet of dead insects on the surface looks like blossom, hence the name Tissa blossom.
Their adult life is short. They can only mate and lay eggs. They wouldn't survive much longer. Their mandibles are underdeveloped, and they can't even feed themselves. So they die, exhausted, after laying their eggs.
The intelligence of this concept is a question that has not yet been investigated. Researchers consider the life cycle and the associated success of the swarm to be unique.
The honeymoon is what has made the tissafly so famous.
As a ranger working at the Hortobadge National Park, Krzysztof Malnasz wants to preserve this natural experience. The individual insects and also the swarm are a spectacular sight. Yet they remain quite harmless. These giant swarms number among the 10 biblical plagues of Egypt. Millions of desert locusts have devoured entire landscapes for thousands of years, and then traveled onwards. Particularly affected areas include Somalia, Ethiopia, Kenya, and Eritrea, and parts of Sudan, Uganda, and Madagascar. This triggers serious famines. In 2020 alone, according to the UN, around 25 million people. But why do locusts in a swarm become such a deadly weapon? It's one of the many questions that Ian Cousin has been pondering for years now. In his adopted homeland, the native Scot is looking for answers.
Locusts are a well-known biblical plague. They can invade up to 1/8 of the Earth's land surface during plague years. They can impact the livelihood of 1 in 10 people on the planet through food shortage. So I can't think of another collective, another swarm that has such an impact on humanity, and yet we didn't understand why they swarm.
Yeah, but actually studying them at low density like this is really important for understanding.
Ian and his fellow researchers know that desert locusts are solitary creatures. In small groups, they're also completely harmless. In a kind of arena, the researchers assemble young locusts before they can fly. Here, the insect's behavior can be better observed. Everything seems peaceful. They keep out of each other's way.
One of the key triggers is when they get hungry and they're short of resources in this environment, they turn on each other. They start to chase after each other and bite each other and avoid others that are moving towards them. Right? So it looks like it's a cooperative behavior, but in actual fact, they're all on a forced march. If you stop, you get eaten.
In the experiment, Ian and his colleague Hannes want to trigger the march. The more insects that arrive, the more aggressive they become, and they bite each other. They run as if they were escaping from something. Ian's analysis reveals that they're doing just that. Within the swarm, it's the fear of being eaten that drives them forward. Harmless locusts are transformed into what Ian refers to as a mobile cannibalistic horde. Does this also happen when they're adults and can fly? That is still unclear.
Our objective is not to stop the swarms ever from forming. It's more to control them, because the locusts are playing a very important ecological role. And so I think removing the locusts, if that were possible, probably not, would actually be detrimental to the environment as a whole. But what we hope to do, if we can predict where and when they will suddenly form swarms, is to prevent that. It's a little bit like a wildfire going out of control. The fire is very important to the ecology of the environment, but we need to control it if we have humans living within that environment.
Ian's team has discovered that locusts follow the laws of particle physics. Their bodies align with each other, like a flowing magnetic field. When many creatures come together, the patterns resemble each other, even in very different swarms.
In this experiment, we'd like to show you videos of 4 different swarm animals. And we want you to recognize which species they are. But you won't see the animals. Your task is to identify the species based on the movement patterns. You will see videos of ducks, of humans, of fish, and of sheep.
And in your assessment of which species it is, we'd also like you to consider the social interactions of the individuals.
The 3 test persons have studied biology. They are experienced observers and have tracked swarms before. For the sake of simplification, humans are referred to as animals, alongside fish, sheep, and ducks. So, what's what here?
And did you find it easy or difficult? How are you doing?
In general, it was pretty hard to guess. I had one correct, which is fish one, but that's the system which I'm most familiar with, so I'm happy to be correct at least with this one.
Well, I got the ducks right, but I confused the sheep with the humans.
But what movements do swarms of fish, bipeds, and quadrupeds have in common?
Many of the movement patterns appear so similar because they're actually following similar rules.
We see hardly any collisions between the animals. They don't swim or hop or run against each other, but keep minimum distances from each other. They orientate themselves towards their neighbor's movement.
So it's these similar rules of behavior that actually make things look similar on the swarm level.
These are general mechanisms that we can observe in all animal species, including humans. It's something that happens in the subconscious, something that evolution has given us, something that we can't control directly, but that has basically matured inside us over millions of years. And now, as a human swarm, we can access it.
We humans place great value on our awareness and on our independent thinking. We see ourselves as the pinnacle of creation. But despite that, can the individual be easily influenced by the group? This is what cognitive psychologist Marcel Brass wants to find out with his students.
Great that you
could come today.
Today
we'll do a replication of the Milgram experiment. So the idea is that you get into your positions, you look up to this building, and then you simply wait in this position for a while, and we'll see whether people follow your attentional orientation.
The experiment dates back to the 1960s. Millions of people followed National Socialism, and the US psychologist Stanley Milgram looked for reasons why, with a series of experiments. Some were also controversial. With this harmless experiment, he wanted to find out whether average people, as he called them, could be influenced by a group and imitate its behavior unthinkingly. Milgram's assumption was that the larger the group, the more passers-by would be influenced by it and also look up into the air out of curiosity. Marcel Brass has identified further reasons.
You see people looking in a certain direction, and that triggers a similar reflex in other people. We don't think that it explains the whole effect. Curiosity certainly plays a role too. People must be wondering about what's actually happening, but we believe there could also be motoric reasons for this effect.
A large group can divert the attention of an individual, quite easily in fact. Obviously, swarm behavior and the herd instinct are also very powerful in us humans too. When it comes to simple actions in particular, many go with the flow. Marcel Brass has developed the Milgram experiment further. He wants to find out whether people can succeed in behaving differently from the group, with the help of virtual reality.
The experiment goes like this. You have to react to two sounds. When you hear a bomb explode, you have to look up to the left. And when glass breaks, you have to look up to the right. The key thing is that you just ignore the group. It's irrelevant as far as you're concerned.
The screen shows what the test subject sees. Although the group is looking in the other direction, she is looking in the right one, albeit with a delayed reaction. Also on hearing the second sound.
Yes, very good. Thank you very much. You always reacted correctly. We noticed that the first time the group looked in the other direction, you hesitated a bit. I don't know if you noticed that too. Did you find it difficult, or was it okay?
I concentrated a lot on the sounds, that's why it worked.
Okay, so you tried to ignore the group, but you couldn't entirely.
The behavior of the group is very dominant as a stimulus.
If a group makes a certain movement, it causes the same action tendency in me. And that's why I imitate the group, even though I may not want to. The more people who do it, of course, the bigger this pull becomes, and the greater the imitation effect. Theoretically, of course, it's possible. Theoretically, if everyone's cheering, I can also remain seated and do nothing. It's just very difficult. It creates a conflict between, so to speak, the tendency to follow the group and possible other actions I might want to carry out.
The forces inside a swarm. If you look closely, you can discover them right on your doorstep. Lime seed bugs originated from the Mediterranean region or Northwest Africa. In the autumn, they gather on lime trees. Biologists call this phenomenon aggregation. The bugs mate and spend the winter in large swarms inside the cracks of the bark. This increases their chance of survival, despite a lot of mass collisions while scurrying around. Off the island of Sylt, mussel beds grow into gigantic carpets. The Pacific oyster originated from a local oyster farm, and from 1964 until today has multiplied here uncontrollably. Gourmets may be delighted, but biologists deplore this as an invasion. The oyster has no natural predators and is displacing the native mussel. Their name says it all. Pine processionary caterpillars also adhere to swarm rule number 1. Stay together when looking for a new tree. Their stinging hairs give us humans rashes, or take our breath away. At the sight of them, animal enemies lose their appetite. Jens Krause and Marcel Brass want to observe how strong these unconscious swarm rules are in groups of people at a traffic light. The man-made rules of the road are known to every child of kindergarten age around the world. Green means go, red means wait. But it's not that simple. Does group contagion actually lead to such rules being broken? Do we jaywalk because others do the same?
Herd behavior or collective behavior is actually always ambivalent. There's the possibility of acting swarm intelligent as well as swarm stupid. If the little red man is showing at traffic lights and people start to cross, that can of course very easily lead to swarm stupidity because you're walking out in front of moving cars. I don't think people are always really aware that the little man is red. They notice that the others are starting to cross, and that makes them follow suit. And often they don't see or realize that the traffic lights are red until later. So they're not consciously breaking a rule. They're just following others in their behavior.
What is striking is that it's slow older people, mothers with children, and young distracted people who do it.
A further possibility is that people may not take the rules so seriously anymore. After all, if others cross the road, then maybe it can't be all that wrong to do so too.
In a collective, rule breaking seems more harmless. The individual accepts the danger against their better judgment. Do they do this consciously or rather unconsciously?
Of course, behavior when crossing at the red light can be contagious. If someone starts crossing, you can literally feel yourself being drawn to follow suit. You can really feel it physically.
And in certain situations, this feeling actually prevails. It probably happens quite often here at the lights because people are naturally impatient. They want to get going. They're waiting for the light to turn green. They're ready to go. And then, of course, this little collective shove by the group reinforces behavior that was already there.
The stimulus to imitate actions has a powerful effect, even on us humans. And it's often more powerful than our common sense, even if that could have dangerous consequences. Uncovering complex mechanisms in swarms and thinking out of the box. That's something that comes quite naturally to swarm researcher Ian Cousin.
Well, understanding how collectives operate tells us about, for example, how our brain works. The neurons are relatively simple, yet coordinating together, they can achieve amazing things. Similarly, elsewhere in the natural world, we see swarms of locusts or schools of fish or flocks of birds. And all of them are benefiting from connecting their brains together via these invisible sort of network of interactions. And that's what I'm really fascinated by. Like, where is intelligence? Is it in the brain, or is it also distributed among these brains?
Ian Cousin has studied schools of fish for many years. The sunbleak, for example. The small common fish hides from predators between riverbank plants. Ian has discovered that schooling fish share their knowledge with each other. The swarm's decision of when and where to flee is based on the movement of individual creatures.
They use different senses. They can feel pressure waves in the water, so they can feel each other, but they also see each other, and vision turns out to be the predominant modality within these groups. And it might be surprising to know that there's no individual that has to lead. Each individual just following simple local rules, looking around, seeing what others are doing, and copying their behavior is sufficient to self-organize the entire system.
For a long time, swarm researchers thought that each individual fish contributed to the solution of a problem. Ian has found that many fish don't even know about the problem, but the school always finds a solution. Using special software, Ian's team has tracked a school of fish and visualized the connections between all its individual members.
We've reconstructed how they see the world and how they interpret that visual information when changing behavior. So if one individual changes behavior, it can be copied by those around it. And so that's what we see here. We see individuals within the group changing behavior, and you can see this wave percolating through the group. And so it sort of represents a spring-like force. When the individuals turn, they influence those around them. That influences those around them, that influences those around them, and that can lead to a few individuals exerting a big impact on where the group goes.
The invisible spring-like force works in every school of fish. For decades, researchers have suspected that swimming in a school must have even more advantages. Chinese scientists, together with Ian's team, have made a breakthrough. Ink flows out of a cartridge under the tail fin of a fish robot. For the first time, the turbulences that each fish generates while swimming become visible. If the neighboring fish adjusts the stroke frequency of its tail fin, this optimizes the flow conditions. In this way, fish in the school save energy. As Aristotle knew, the whole is more than the sum of its parts.
We discovered in fish schools initially that actually uninformed individuals, those that don't know what's going on, but are participating in the decision-making, are incredibly important. They actually prevent an extremist minority, a strongly opinionated minority, from dominating decisions. And then we thought, well, I wonder if that could also apply to humans. And indeed, it also seems to be the case that having individuals that are not strongly opinionated within a decision-making network is really important, allowing each side to begin to exchange information. It prevents polarization and allows groups to make better decisions.
Anna Nassauer is a violence researcher, and she knows that people in the swarm do not always make the better decisions. Like on August the 31st, 2020. Different interest groups oppose the state's protective measures against COVID-19. Fascist slogans are also chanted. Conspiracy stories are doing the rounds. Apparently, Donald Trump has come to Berlin to liberate Germany. Fake news is circulated. German police officers have apparently defected to the Russians. The situation escalates. Around 400 Reichsbürger, esotericists, conspiracy theorists, and neo-Nazis all storm the steps of the Reichstag together. It's only when enough police officers arrive at the scene that they succeed in stopping the swarm.
What interests us in demonstrations like the storming of the Reichstag is, what role does the swarm, the mass, play in the behavior of individuals? Do people in a group allow themselves to be emotionally infected by others? What motivates people to join in, and what part does that play in escalations? What role does mass momentum play when so many people meet up?
To understand why a situation gets out of control, the violence researcher takes a closer look. With a breach of the rules as serious as this one, there's rarely just one explanation as to what forces are at work and what takes place in such groups. What's more, certain group dynamics don't always conform to first impressions. As with these peaceful-looking meerkats. When it comes to arguing, they're real champions. The main objective of the meerkat group is to search for food. Where can more food or better food be found? Which feeding place is easier to guard? And who's allowed to burrow where? They argue fiercely over such decisions. Social researchers refer to human societies with such principles as defensive democracies. With meerkats, arguing does no harm. On the contrary, it's useful. Due to different interests, the decision makers in a group make different mistakes. That is much smarter than if everyone made the same mistakes. It's similar to our democratic principle. Overall, different errors tend to balance each other out, and the quality of decisions increases. It's the 1st of May in Berlin, Labor Day, when trade unions and other social groups traditionally demonstrate for more social justice. In the swarm, demands are more likely to be heard. Since 1987, violent clashes between police and demonstrators have occurred time and again. Anna Nassauer investigates when and why violence erupts at politically motivated demonstrations. Every year at Mariannenplatz, citizens' initiatives, with their cheerful Maifest, form a deliberate contrast to the riots of the past.
It was long assumed that potentially violent people were present at demonstrations and that this could escalate things, as could certain police strategies. Yet comparative analysis have shown that this isn't the case. What's really relevant is what happens in the actual situation. There are many demonstrations where people are ready to use violence, but things stay peaceful. Because the crux of the matter lies in the actual situation itself and in the way people behave during these demonstrations.
Research proves it. Violence actually breaks out in only about 2% of all politically motivated protests in Germany. Wearing masks is considered a sign of escalation, as the researcher calls it. That applies to both sides. People take up position. A further sign of escalation: smoke bombs.
And there are 4 more mechanisms that have an escalating effect. They include damage to property on the part of the demonstrators, for example when protesters set fire to rubbish bins or smash windows. Another escalation factor is mismanagement on the part of the police. If they're no longer able to communicate with the units, for instance, or lose their overview of the situation. A further relevant mechanism is territorial encroachment. When one side encroaches on the territory of the other, for example when demonstrators leave the route and try to occupy a nearby square, or when the police move into the demonstration route. And a final mechanism that escalates things is communication problems. When the two sides can no longer communicate with each other, or communication is cut off.
If any of these factors come together, trust is lost on both sides, and that acts like an accelerant.
What we see systematically is that this leads to tension and fear, both among the demonstrators and among the police, and then the situation boils over and escalates.
Many media and the police already classify property damage as violence. Social researchers regard it as a protest tactic, to gain more media attention for a cause.
I define physical violence between people as when a person is injured or in the worst case killed. It's very important to keep a clear distinction here, because one thing might lead to the next. Property damage can have an escalating effect and lead to physical violence. We know from research that both have different inhibition thresholds.
Violence arises spontaneously, usually at moments when people are overwhelmed. That occurs when the routines that both sides normally rely on break down. Chaos, confusion, and fear start to spread.
There are several emotions that some researchers say are universal. We can read them in people's faces around the world, and they include joy and fear. What interests me specifically is that many demonstrations start out peacefully and very relaxed, and then escalate after tension and fear have increased dramatically. You can see that in people's faces and their body language.
Violence is not something hormonal. Rather, attacks are initiated by intense emotions. Aggression makes the attacked person feel cornered. Loss of control creates fear.
My research shows that fear is an emotion that is far more strongly related to an outburst of violence than aggression or anger.
Peaceful togetherness or violent altercation. With humans, this transition from one state to the other is a fluid one. Within a group, the behavior of many swarm systems is stable yet flexible at the same time. With fish too, it is not yet clear how they manage this balancing act so lightning fast. A single fish sees attackers with about 60% probability. A school with almost 90%. That's a huge difference. The school of fish organizes itself. That way, it makes use of the opportunity to behave more intelligently, despite the supposed superiority of the attackers. Swarms of people sometimes fail to make use of that opportunity, and that harms everyone. Using VDA, video data analysis, Anna Nassauer reconstructs exactly when violence breaks out at politically motivated demonstrations. She analyzes interviews with demonstrators and police. She uses satellite images to find locations where hundreds of social media videos originated. She looks at images from surveillance cameras and the press. From all these sources, the sociologist pieces together a detailed picture. Here of riots at the G8 summit in Rostock in 2007.
What we see is that strategies and motivations can change a great deal as things progress. In Rostock, for instance, the police started out with a tolerant strategy until they felt that demonstrators were not sticking to the rules. And we see the same on the demonstrator side. Many of them were demonstrating peacefully until they got the impression that the police were toying with them and trying to provoke them.
Massive communication problems between individual police units and between police and demonstrators exacerbate the situation. For no apparent reason, a police car blocks the announced route. This territorial encroachment leads to a massive outbreak of violence, with almost 1,000 people injured on both sides.
Interactions in the course of the demonstration are really key here. It's through these interactions between demonstrators and the police that interpretations on both sides change. Each group, demonstrators and police, each swarm, if you like, draws closer to the other. That really escalates things, and that's when demonstrations boil over.
How and with what means protests are carried out also differs from one country to the next.
For example, in France, there's a longer tradition of building barricades, while in Germany and the USA, there was a parallel development in the 60s of so-called sit-ins as a form of protest. What interests us as researchers is seeing similar patterns in the course of the interactions and in the swarm behavior, which then lead on to escalation.
Many people working together for one cause can also create great things. Around the globe, many people continue to fill one of the most popular websites in the world. In 315 active languages, Wikipedia is clicked on around 5.5 billion times per month. The online encyclopedia is also better than its reputation. One study has placed it on a par with the Encyclopedia Britannica. There is one small drawback. Fewer than 10% of all authors write 90% of the articles. The platform is also becoming increasingly relevant for scientists. A wisdom of the many is asserting itself. So, are swarms smart or not?
I think what's very impressive about swarm intelligence is that it enables the group to solve problems that an individual can't solve in that way.
Intelligence is always something that occurs in a certain context. That means that it's tied to the situation. In a certain situation, a behavior is intelligent, and in other situations, it just isn't. And I think the same applies to swarm intelligence.
With groups of people, sociologists assumed for a long time that being emotionally affected made people more stupid. That is, made them act irrationally and thus not in their own best interests. And now we've discovered that people who get emotionally affected within a group do still continue to be rational, because emotions simply help them to evaluate the situation better.
And yet, when we have a certain problem and a social group, it remains very difficult to predict a priori Whether they will really develop swarm intelligence in a situation or fail to do so. It still can't be predicted directly, and I always find that amazing. Even though we already know a lot about such processes, it's still difficult to make predictions.
Swarm behavior is frequently smarter. Sometimes it isn't. The forces at work within a swarm are still very much of a mystery.